Hi everyone, we are back and we are going to do our 3-point bending problem in Mathematica. So let's actually pull up our Mathematica and let's move through with this solution to look at again, how does the deflection look like, what's the bending moment diagram, what's the shear moment diagram, and then calculate maximum values of stress and all those good values. So while this loads up, we see that we have a 3-point bending test. So we have a pin here, and then we have a force applied basically right down the middle. Let's just say the force is 10 newtons as usual. So we can have our expression, again, Dirac delta function applied halfway through the length of the beam. Because we have the pins here, we know that we are going to have a boundary condition at 0, which is going to be equal to a boundary condition at L, which will be no deflection. Additionally, we know that the moment, basically here and here, will also be equal to 0. Fantastic. So we can go ahead and we can proceed. Let's open up our beam bending. Let's define our parameters for our mythical, or not mythical, but our theoretical beam. And I'm actually going to go ahead and change some of these parameters here for the cantilever just to kind of practice. So it's going to be Dirac delta L over 2. I am going to be y at 0, 0, y double prime at 0. I'm going to just ignore this because it's going to be 0 anyways. And I'm going to say the same thing here, and then again, my y at L, excuse me, y at L is going to be equal to 0, the displacement. So those are these are initials. It should be boundary conditions. So here we go. Now we can look at the deflection of our beam. I should call that deflection, but again. So we can look at our solution. Makes sense, we're pinned. We have that force applied there. We'll make sure that we're also minus L over 2. Perfect. So we've got that. We can find the minimum again. And that should be at half the length of the beam, 0.25. Excellent. And you can also find it, elsewhere. So we can see where the maximum deflection is. If we were to kind of put it in the opposite direction or pin it, we'd have to go up or find maximum. So just be aware of that. Minimum will actually mean like literally minimum value. So shear diagram, y times I times our solution, moment diagram. So we can let's look at our shear diagram first. So we can look at our shear. We can see that two-step, that discontinuity, obviously. And it makes sense when you look at kind of your resultant forces. And we can see a value here. So we can see the moment, actually see the shear moment there. So our moment is maximized right there at that center. Makes sense, we're bending. Also, it makes sense that it's positive, right? So if we look at that, when we bend this beam, it's going to look like this. So positive moment. Nice. And if we look at where the moment is maximized, again, we still have our y. So if I look at here, this is tension now on this side, and then this should be in compression. So if I plug in, for example, our moment is minus moment, and then we're going to set it at 0.25, so the x value. So if I do it at h over 2, positive, I'm compression. If I do minus h over 2, I'm in tension. We got it. Maximum stress. So we are good to go. Fantastic. So, again, isn't this a lot nicer than having to make cuts and do all these different do these things? I hope it is. I hope it's enjoyable. We're gonna do one more problem together with a distributed load, and then we'll see you all in the next module, which will be buckling. So see you then.